Imagine dropping a detective into the middle of this massive overgrown forest.
Yeah.
And you hand them a single puzzle piece, right? And it's written in a foreign language. You don't give them a map. And you basically ask them to solve this complex murder mystery using only, like, scattered clues buried under the dirt.
Sounds pretty much impossible.
Right. But that is essentially what we're doing when we ask artificial intelligence to perform frontier science. We're taking these systems that are, built for summarizing clear, organized facts, and we're just throwing them into the chaotic, fragmented reality of the absolute edge of human knowledge. So welcome to today's deep dive.
Yeah, glad to be here.
We've got our hands on a really fascinating technical report today detailing a new framework, and it's called SciResearcher. And our mission for this deep dive is to explore this fundamental shift in how developers are, trying to change the way AI actually thinks.
Yeah.
We're looking at a system that's designed to transition AI from being this fast, shallow fact retriever into something that's slow, deliberate, and like a deeply patient scientific thinker, which is a huge deal for you, our listeners, because it changes everything about how we're going to interact with information.
It really is. I mean, it represents a massive architectural leap.
Yeah.
We're talking about the difference between a machine that acts as a well-indexed encyclopedia and a machine that genuinely learns how to tolerate doubt.
Wow.
Yeah, it learns to handle frustration and iteratively test hypotheses, just like a real autonomous resource scientist.
Okay, let's unpack this, because to really grasp why a framework like SciResearcher even needs to exist in the first place, we have to look under the hood of how current language models actually work and, why they fail so spectacularly when you ask them to do real science.
Right.
Because you might be wondering, like, why can't we just feed an AI a million medical textbooks and expect it to cure a disease?
I mean, that's the dream, right? But the problem isn't the volume of data. It's the lack of connections between those data points.
Exactly.
The report makes a really crucial distinction here between general knowledge and frontier science. So general knowledge is what they call hub-centered and densely linked.
Hub-centered.
Yeah.
Yeah.
So if you ask an AI about, say, a famous historical event, it relies on this incredibly robust network of standardized information. It's practically a city with this intricate, perfectly paved highway system, right?
Like a Wikipedia page.
Exactly, like Wikipedia.
Okay.
It has predictable categories, dates, locations, primary figures, and all of those data points link back to other heavily trafficked centralized pages.
And current AI models, they thrive in that environment because they are fundamentally just prediction engines, right?
Right.
They rely on the statistical probability of the next word. So in a densely linked city where, every road leads to the town square, predicting the next logical step is super easy.
Yeah, it's trivial for them.
But then we step into the messy forest of frontier science. And the paper describes this as sparsely distributed and weakly linked.
Yes.
So if we stick with the analogy, this is a city where literally none of the roads connect, and you're forced to build your own bridges just to get from one neighborhood to the next.
Right. The information simply lacks a canonical entry point. There is no homepage for, like, the cutting edge of oncology or advanced physics. Let's say you're looking at a specific genetic mutation that's relevant to lung cancer.
Okay.
The paper actually uses the example of the EGFR T790M mutation.
That is a mouthful.
Yeah. It is. But the point is, there is no neat little info box summarizing everything that mutation does across every possible scenario.
Right, because its meaning is completely dependent on the context.
Exactly.
It might mean one thing in, like, a first-line treatment setting and something entirely different after a patient has developed resistance to a previous drug. And the clues to figure all that out are just scattered everywhere.
They really are.
You might have one piece of the puzzle in an academic paper from, 5 years ago, and then another piece is buried in the supplementary materials of a completely different study.
Oh yeah, those PDFs nobody wants to read.
Right. And maybe the final piece is hidden inside a raw clinical data set. It's like trying to build a house when you're used to having a really clear blueprint, but suddenly you're just dropped into a forest and told to find random conflicting materials.
That's a great way to put it.
Yeah.
And none of those sources naturally talk to each other.
So if the information is so scattered and lacks a homepage, how does an AI even know where to start without just, guessing or hallucinating?
What's fascinating here is that because there is no canonical entry point, deep research agents must be explicitly trained to navigate this sparse ontology. When an AI encounters this weakly linked data, its core mechanism predicting the next most likely token It just breaks down.
Because it can't see the path.
Right. Because there's no clear statistical pathway between an obscure supplementary table and a 5-year-old clinical trial, the model can't easily jump from A to B. So it does what language models do when they get confused.
It confidently hallucinates.
Exactly. It builds a brute to nowhere. Left to its own devices, it just guesses based on the phrasing of your question.
Which tells us that to navigate this sparse ontology, the machine really needs to be taught patience.
Yes, exactly.
And it has to learn how to wander through the forest deliberately, recognize when a clue is a dead end, and synthesize fragments of information across long stretches of time.
And that is exactly the gap SciResearcher aims to fill. It doesn't just, tweak an existing AI model. It builds an entirely new, highly automated pipeline to generate these grueling training data sets.
Just to force the AI to become a scientific detective?
Right. Since the AI can't rely on scraping clean, standardized web pages anymore, this framework constructs its own rigorous training ground. Let's look at how this automated data pipeline specifically builds these complex conceptual tasks.
Okay, yeah, let's break down how this automated curriculum actually works. They start with something called seed entity acquisition, right?
Correct. They filter massive public data sets to isolate the top 5% of scientific entities. And they're judging them based on their relevance to frontier science, their concreteness, and their specificity.
So they're not looking for generic stuff.
No, the goal is to start with highly specialized concepts, not just generic biology terms. Once they have that seed entity, the system deploys a web agent to browse live academic sources, extract verifiable evidence, and form a base question.
But a straightforward base question isn't enough, is it?
No, it's insufficient for teaching deep reasoning. If the answer is easily searchable, the AI will just fall back on its fast retrieval habits. It'll just look it up.
Here's where it gets really interesting, though. That leads to the next step, which they call anchor-based augmentation. And I want to try and explain the mechanism here because it fundamentally changes how the AI interacts with the text.
Yeah, go for it.
So let's say the system's base question is about how a specific vitamin, like pantothenic acid, binds to a highly specific protein like IGF-BP6.
Right, a very standard biological interaction.
Yeah. But if you feed that question to a standard AI, it will just search for those two names together and parrot back whatever sentence happens to contain both words. It takes a reasoning shortcut.
It's just surface-level pattern matching. It doesn't actually understand the relationship between the molecules. It just knows, hey, these two text strings frequently appear near each other in my training data.
Right. So, to stop that shortcut, the SciResearcher pipeline scrubs the names entirely. It extracts a key anchor entity from the question and sends another web agent to find evidence about that anchor and then fuses it back into the original prompt.
It hides the clues.
Exactly. Instead of naming the vitamin, it replaces the name with its side effects, describing it as a vitamin whose antagonist-induced deficiency causes acute encephalopathy. Yeah, and it scrubs the protein's name, too, replacing it with its molecular shape, noting that it has 5 end-domain disulfides, so this fused quotient is insane.
It's a multi-hop nightmare is what it is. It forces the AI into a process of secondary discovery. Before it can even attempt to answer how the two molecules interact, it has to launch independent research queries just to figure out what those cryptic descriptions are even referring to.
It effectively turns the prompt into a multi-step game of scientific jeopardy. But I have to ask, does making the phrasing this convoluted actually stop the AI from taking a reasoning shortcut? Like, what stops it from just making an educated guess based on the complex vocabulary?
Well, the researchers anticipated that exact vulnerability. The generation of the question is followed by a rigorous post-processing phase designed specifically to close off any of those remaining loopholes.
How so?
The system performs textual obfuscation. It ensures that the wrong multiple-choice answers, the distractors, are perfectly balanced and logically plausible, and it runs diagnostics to confirm that the hidden evidence definitively entails the claim.
So it systematically removes the AI's ability to just guess.
Right. By forcing the AI through these hidden clues, the framework demands what the paper calls long horizon browsing. The AI has to sequentially access multiple independent academic sources just to synthesize the final answer. It learns that stopping at the first page is almost always a trap.
It's basically an artificial environment designed to induce frustration.
Yeah.
Forcing the machine to show its work step by agonizing step. But, being a scientific detective isn't just about stringing together facts. Knowing what a chemical does is pretty much useless if the AI can't calculate how much of it will kill a tumor over an 84-day period.
Exactly. Real frontier science requires heavy computation.
Right, which naturally leads us to the second half of the framework, computational task curation. Because navigating concepts and linking unlinked clues is only half the battle.
Frontier science involves dynamic, shifting systems. In fields like computational biology or advanced physics, you aren't just looking for static facts, You're modeling change over time.
Yeah.
So the web agent for this pipeline doesn't just hunt down textual evidence. It hunts down advanced mathematical models.
And the report highlights a staggering example of this. The agent extracts an ordinary differential equation, or an ODE system.
Which is no joke.
No, this isn't a generic algebra problem. It is a full clinical model tracking tumor cell volume in a patient with a specific grade of brain cancer during a course of temozolomide chemotherapy.
Over 84 days.
Right, over 84 days. The math has to account for the patient's dosing schedule, the proliferation rates of the cancer cells, and the decay rate of the drug in the bloodstream.
But generating a text-based question from that math is one thing. The critical hurdle here is verification.
Right.
Because if an automated AI system generates a highly complex, novel computational scenario, how do you verify that the underlying math is actually sound? An AI can easily write a believable paragraph about a tumor shrinking, but math requires absolute internal consistency. If the input parameters contradict the laws of physics, the whole model falls apart.
So to solve that verification problem, the framework uses something I kind of think of as the five-solver test.
Yeah, that's a good way to frame it.
To verify that the newly generated math question is actually valid and solvable, SciResearcher samples 5 different Python solvers created by proprietary large language models. So it essentially asks 5 different AI scripts to write the code needed to solve the problem.
And the outcomes of those 5 attempts determine if the question makes it into the training curriculum.
Right. If all 5 solvers return the exact same perfect result on the first try, the question gets tossed out.
Because a problem that is trivially easy for 5 independent scripts to solve is not pushing the boundaries of scientific reasoning, is not teaching the model anything new.
Conversely, if all 5 solvers return syntax errors, or if the code crashes, the question is deemed broken or unexecutable and it gets tossed again.
Yep.
And if all 5 return completely wildly different mathematical answers, the question is considered too unstable, tossed. The sweet spot they're looking for is found using majority voting over the solver outputs.
And this is where we have to understand why majority voting is the gold standard for this kind of training. If 3 solvers arrive at the exact same mathematical conclusion and 2 solvers completely fail, it proves 2 things. First, it proves the problem is difficult enough to cause failure, so it demands genuine complex reasoning.
Right.
Second, it proves that despite the difficulty, the problem is grounded in objective reality and has a definitive, achievable answer. It pushes the AI to the very edge of its capability without handing it an impossible task.
Okay, I do have to push back on the methodology a little bit here, though. Wait, so we are essentially using AI to grade other AI's math homework.
Basically, yeah.
I would think this risks creating a massive echo chamber where the AI simply reinforces its own flawed logic, right?
Well, here, if
Prioritizing consensus over actual scientific truth.
If we connect this to the bigger picture, that concern highlights exactly why the specific mechanism used here is so vital. They are not relying on text generation, like LLM vibes, to check the math. The system actually executes the Python code in a true computational environment. It runs the numbers. The filter relies on objective mathematical consistency across independently generated scripts.
Ah, I see.
Yeah, if the logic the AI used to build the equation is flawed, the code will just crash, or the variables will contradict each other. The execution grounds the problem in real executable computational logic, ensuring that the AI is learning actual quantitative reasoning, not just learning how to confidently generate text that looks like a math equation.
Oh, that makes sense. It isn't just predicting the next word. It's writing a program, running the program, and objectively verifying the output against the constraints of mathematics.
Exactly.
So we have this dual pipeline. We've got the conceptual curation forcing the AI to build bridges across unlinked data, and we have the computational crucible forcing it to run rigorous mathematical models. The ultimate question is, did this automated curriculum actually work?
Right.
When they took a base AI model and trained it on this grueling data, what happened? Let's look at the benchmarks.
The benchmarks are highly revealing. The researchers started with a relatively small open-weight model known as Qwen3-8b. And by applying their framework, they created what they call SciResearcher 8b.
Okay.
They then subjected this newly trained model to the HLE Biochem Gold benchmark.
And for context for you listening, HLE stands for Humanity's Last Exam.
Which is quite the name.
It really is, but it's a benchmark specifically designed to move past standard trivia. It's meant to be so difficult that only human domain experts, people with deep academic backgrounds in these specific fields, can typically solve the problems.
Right. And on this incredibly difficult benchmark, SciResearcher 8B achieved a 19.46% accuracy on its very first try, which is a metric known as pass at 1.
Okay.
And given 3 attempts, or pass at 3, its accuracy climbed to 31.54%.
I mean, to someone used to thinking in terms of high school grades, 19% might sound like a pretty massive failure, but in the context of humanity's last exam, administered to a relatively small 8 billion parameter model, that score is stunning.
It's a massive achievement.
The report points out that this small model significantly surpassed much larger proprietary agents. It beat an agent called SciMaster, which uses the massive GPT 4.1 backbone.
Yeah.
And it even approaches the performance levels of OpenAI's dedicated deep research system. Furthermore, they saw enormous 13 to 15% absolute gains on other brutal expert-level benchmarks like Super GPQA Hard and TRQA literature.
The raw scores are impressive, yeah. But the fascinating finding regarding the agent's behavior is really the most important takeaway here. The training didn't just cram more facts into the model's weights.
Right.
The reinforcement learning applied over these complex tasks induced a profound behavioral shift in how the machine actually approaches problem solving.
The data on this is wild. The researchers tracked the internal operations of the AI during testing, and they found that after undergoing the SciResearcher training, the AI took trajectories that were 0.3 to 2.7 times longer than the baseline model.
It slowed way down.
It learned to dynamically adapt, yeah. On the conceptual questions, it took an average of 7.74 macro steps to reach an answer. But on the harder computational questions, it averaged 9.14 macro steps.
And we should clarify, a single macro step in this architecture is not a simple action. It involves a whole sequence of underlying processes: planning a query, executing a web search, reading the retrieved documents, evaluating their relevance, and deciding what to do next.
So it's doing a lot of heavy lifting.
Exactly. Taking 9 macro steps means the AI is engaging in a sustained, highly iterative research loop. It checks a source, realizes it's missing a piece of the puzzle, formulates a new search, runs a quick calculation to verify a variable, and then integrates all of that back into its main hypothesis.
So what does this all mean? Looking at this behavioral data, the narrative of the entire framework really just snaps into focus. Because SciResearcher didn't just teach an AI scientific trivia. It literally taught the machine patience. It taught it persistence. The AI is behaving remarkably like a human PhD student who slowly learns that you just can't rush a complex literature review.
You really can't.
You have to tolerate the frustration of dead ends. The AI learned that taking the long, slow way around the forest is the only mathematically sound way to solve frontier problems.
It cultivated an adaptive, long-horizon, information-seeking behavior. It fundamentally unlearned the instinct to just guess the next token and learned to build logical bridges instead, which proves that we can automatically generate the environments necessary to teach AI the scientific method itself.
Which brings us back to why this matters to you as you're analyzing this landscape of technology and information. You might be wondering what the practical application of a 19% score on a specialized science exam really is.
Right.
It matters because this research fundamentally shifts what it means to be well-informed. We are moving past the era where AI serves primarily as a fast but shallow fact retriever that just, summarizes a Wikipedia article you could have read yourself.
The barrier to entry for understanding and utilizing dense, cutting-edge information is about to drop significantly. In the near future, your personalized automated research assistants won't just look up answers.
No.
They will synthesize deeply fragmented reality. They will autonomously cross-reference unlinked clinical datasets, dig into the supplementary tables of obscure physics papers, and build the conceptual bridges necessary to generate entirely new insights for your own work or curiosity, all functioning quietly in the background.
We are transitioning from fast talkers to slow thinkers, but looking at the architecture of the SciResearcher pipeline leaves us with a provocative final thought to ponder.
Okay.
If we now have automated frameworks capable of generating these mind-bending, multi-hop scientific scenarios purely to teach an AI how to tolerate frustration and make it smarter, what happens when these deeply patient, long-horizon AI agents start using those exact same skills to formulate entirely new scientific questions?
Oh, wow.
Right, like Questions that human scientists haven't even thought to ask yet. If the detective in the forest learns exactly how to piece together the most complex, unlinked mysteries humanity has to offer, how long is it before that detective starts writing the mysteries?
It forces us to completely reconsider the limits of autonomous discovery.
We'll leave you to think on that. Thanks for joining us on this deep dive.